Hello, Bhavna. Am I audible?
Yes, sir.
Okay, Bhavna. So in the yesterday's class, I covered till you introduction basically till what kind of motions we have. So where we discuss about 1D motion, 2D motion, so on, so on. Then translatory motion and the rotatory motion, right? There's one more motion that is oscillatory. Oscillatory is basically a to and fro motion. Okay, it's kind of repetitive motion along some fixed path. You can assume that as an oscillatory motion. Okay, that is we have three kind of motion. Let's move to the main chapter topics. Okay, first thing is position vector. Um, Bhavna, we have already did the vector completely, so you might be aware with the position vector, right?
Yes.
Okay, so first is position vector. Position vector. What this vector does is it this vector points in a space whose coordinates are x, y, and z. Okay, then you can know the position of your particle of your object with respect to origin, like position at this particular point with respect to the origin. Okay, this
Okay,
points
sir.
position vector points towards a particle in space. Okay, represented by x, y, and your z as a coordinates. Okay, so this x, y, and z, these x, y, z coordinate uh, yeah, gives you position of particle, gives you position of particle with respect to position with respect to origin. Okay, and what is the origin coordinate of the origin?
Zero.
0, 0, 0, because we are taking all the three directions. So yeah, I can simply say if I have to make a coordinate like this, so I can say this is your x, y, and this is your z, the third one. So it goes on like, so this is your you can assume it to be the y-axis, x-axis, and z-axis. Okay, so you have three axes. So I assume this is a point I have pointed out. It might be one. This is second. Basically, in y you have second, two direction, and in z you can have. Okay, let's make one as three. Oh, z as one. and x has 3. Okay, so yeah, what is the points you have? Let's say this is your x-axis. So 3, if I'm saying this much is 3, this much will be somewhere around 2, and this much will be 1. So you have got this is a point. This is a position vector. Clear, Bhavna? This point. This is origin. From with respect to this point, you have this as position.
Yes, sir.
Okay, that is the point. So I'll just remove it for a while. Simply I'll join this one, which I made in earlier places. Okay. Displacement vector also we have done, right? Yeah, also one thing, you can represent this position vector with any random variable. Generally the variable which we use is generally r. Okay, because this is a vector quantity, so you can write this as r. Either you can use s, no, yeah, that is fine. R you can use, or p you can use. These two variables you can use. Okay, it's a good thing. Yeah, so this contains all the three directions, so you have to write x in I plus y in j plus z in k. Okay, these are the three things which you have to remember. Clear, Bhavana? Now the next thing is displacement vector, right? And we have already done the displacement vector also. So here we come to the displacement vector. Displacement vector. What is the displacement vector, Bhavana? Bhavana, what is the displacement vector? A vector joining two points in a space. Okay, two points in a space. In a space. Okay, where initial to final gives um, where the points are initial and final point, you can say, where points are initial position vector. Okay,
Which gives change in position of an.
yeah, which changes position. Okay, initial position vector and the final position vector. Okay, and the final. So you can simply say that you have two position vector. One is this one. This is one position vector that you can say R1. Okay, represented by this vector. This is another position vector R2. Okay, so you can simply say this is the line joining for you from here to here. This results you the position vector, right? And what is the value for this position vector? Bhana, what will be the value of this position vector? You can represent this as R12. Okay, whatever, it's your assumption. Okay, this R1
Okay.
to 2 or 2 to 1 is your assumption, how you want to write. What happens is sometimes people say that I am at the 1 and I am going towards the 2. Okay, so some people like this. Okay, some people understand it in another way. Some says that okay, I have reached 2 from 1. Clear? So it's your assumption, whichever you want to take. You should just know you should just don't mug up that this results R2 minus R1, okay? Because sometimes what happens is the statement is like 2 to 1, but this representations is kind of different thing, okay? So the students who have mugged it up that if R12 is written, I can simply do R2 minus R1. If R12 is R21 is written, I will do a 1 minus 2. Okay? So this makes sometimes difference with textbook to
Obviously.
textbook. All right. So simply we can say that this is basically change in vector. Okay, change in vector. Uh, although
Obviously.
I prefer putting change in vector. What is the change in position? Basically, you can say, na, this is nothing but change in position I'm looking for. Right. So what is the change in position? R2, R2 vector minus R1 vector. Right.
Yes, sir.
R1 vector. Okay. If this now this vector representation, it's up to you, okay, whatever you want to say. You are going from R1 to 2, 2 to 1, okay. This we use in case of when we have to deal with both directions, r like from this also, okay. So in that case you can see with only delta r I'm not going to get what does this represent, right? So that's why we specify by using R12 or R21. That is the case. Okay, if I ask you the magnitude, so yeah, magnitude will remain same. R21 magnitude equals to R12 is equals to delta R, right? Can I say this?
Yes.
Because magnitude is this the distance, and distance is same whether you go from here to here, whether you go from here to net distance, okay? In a straight path. This
Obviously.
is what I'm saying. So this is your displacement vector. I think this is also clear. Now we can go and look for the distance and displacement values, okay? So Bhavna, what is your displacement? Displacement is nothing but a vector drawn from initial to the final. Earlier we were talking about the vectors. Okay, with respect to vectors, what is displacement vector? What is position vector? But now the topic comes into the main core of the kinematics, where we have to talk about what is the net displacement of the particle. Okay, so you can say
Shortest distance.
the shortest distance, right? Something like that. So let's come up with distance and displacement. Let's see. Wait, it's not wrong. Bhavna, can you hear me? Hmm, okay, I think you are
Yes,
the
sir.
co-host. Okay, my two screens are already visible. Okay. All right, Bhavna, whatever I have written that has been erased. Okay, so yeah, that's fine. Okay, no problem. We are starting with the distance, the main part which we didn't write here. Distance. Okay. This position vector and the displacement vector has been erased, which you already know very well. Distance and displacement. All right, now. So what is basically the distance? The shortest path, right? Shortest path between your initial and final point of travel. So displacement, shortest path between your initial and final point. Initial and final position of vector. Initial and mm, final position in your motion or whatever in your motion. That is fine. Okay, how we can represent this thing? One thing we can do if you want to, if we are given a velocity, we can say a particle is there and it is moving with some sort of velocity. So what can be the displacement? You can simply go and say, sir, I can get the displacement as displacement generally shown by this s. That will be nothing but the vector times of dt. Okay, this is basically the integration of the this thing. Okay, so further you can just write the v or v vector as v velocity in the x direction, velocity in the y direction, velocity in that so on. So okay, this is what the displacement will
Yes.
be. Now your question might be, sir, why we are integrating this, right? So Bhavana, if you just go back and remember one thing, when we study the integration, using integration you get some sort of area, right? If
Yes.
I just make two a plane axis something kind of thing. So if I say, if I wanna just get my integration of this portion, okay, basically this is y, and for very small strips dx, you have to integrate, right? So how you do? You will simply say, sir, I will put y, I will put x dx, and from this, like wherever, what are the range you will see, I will go like this is the range x1 to x2. So I will go from x1 to x2. Okay. So Bhavna, basically what happens is, okay, just remember this part. I will tell you why this relation comes good. The reason is when you make a velocity and time graph. Okay, let's discuss this part also. If you could remember your 10th, 9th grade where you have studied about the graphs, you know that a velocity time graph, the area of a velocity time graph gives you the displacement, right? Area under the curve in velocity time graph gives you displacement. Okay, time graph gives you displacement, right? Is this clear, Bhavna? Yeah, have any doubts there? Any queries there? Any kind of query?
No, sir.
Yeah, like if you have any query in this part, you can let me know because we will discuss this part again also. Okay. The next is distance. Bhavana, you know, distance does not depend upon the direction, right? It solely depend upon what is the real value of your motion,
It
right?
is
I
a
can,
scalar.
yeah, it is just a path, actual path covered, right? So this is the actual path, actual length of path traveled.
Total path length from
Yeah,
initial
to
point to the final.
actual length of path travel. Okay, this is the thing. So I can simply say that to get this distance, I will go and simply integrate it with v magnitude. Okay, assume you are given a velocity. If speed is given, no worry, you can simply do speed into distance. Okay, but instead of speed, if you are given a velocity, you can simply do one thing: get the magnitude of that velocity and just do the integration of time. Okay, and you know time also always goes positive, so you can do this, right? Clear, Bhavna?
Yes, sir.
Okay, so just some points are there I want, right? I'll just explain it. First of all, distance is a kind of scalar quantity, okay? Displacement is a kind of vector quantity, and you know the reason behind that both, right? Distance between the initial and final point can have infinite number of values, but a displacement will always be having a unique, okay? What does this mean? That
Obviously.
assume these are 2 points which you are supposed to travel. Maybe this, maybe this. So what is the displacement? The only displacement is only is this one, right? If you have started from here, if you ended here, and if I ask you
Yes,
what is
sir.
the displacement, the only this is the vector. Even if you just if you say this is the vector, now still this is a different thing, right? This is a
Only in a
displacement.
straight line path.
Yeah, this is a only straight line path. I'm just saying that you can still
Mm,
here you can have two direction, but if you just write instead of this direction, if you make it like this, so it will again change the displacement, right? It will, this assumes this is your initial, this is your final. So for any particular initial and final, you have only one unique displacement. Is that clear?
okay.
But if I ask about the distance to reach this from here, to reach this point, you could have traveled like this also, you could have traveled like this also, like whatever n number, like infinite number of points are there. Okay, you can be like just make a round and you can reach here. So basically infinite number of distances are there to reach a certain point from another certain point, right? This is another thing. Another part is about displacement. Yeah, displacement can be negative, can be zero, and can be positive as well. But when we talk about the, yeah, yeah, when we talk about the distance, it
It
can
is
zero
only
mean,
positive.
yeah, it will only positive or zero. When we say it is zero, it means your object has not even started moving. Okay,
It
where
is
it
at
was,
rest.
yeah, it is still, it is at the rest. Okay, so I can simply say if there is a motion, if there is a motion, any kind of motion, the object will always be having a positive distance, not even zero. Zero distance says that the object is not in the motion, it is in the rest state. Is that clear, Bhavana?
Okay, sir.
All right. So yeah. Now the magnitude of displacement. Okay, I can simply say that magnitude of displacement can never be greater than. So you know this is what my representation of displacement was. The magnitude of displacement either will less than or either at max will equals to distance. Okay, this is the case. Either the magnitude of displacement will less than or at max it will be equals to. When it will be equals to? When your particle has just have traveled in a single direction in a straight line. Okay, in that case your distance and displacement will equal, otherwise in all cases it will be less. Is that clear, Bhavna?
Yes,
In
sir.
all other cases, it will be lesser. Okay. In uniform motion, the displacement and distance remain same. Why we say a uniform motion? Okay. What we understand by a uniform motion? A motion where particle did not change its velocity, right? It means the particle did not change its direction. It means it is just moving in a straight line. So in that particular case, you can say that displacement distance goes equal. Okay. Displacement
Okay.
returns, displacement becomes zero when your particle completes a one cycle. Cycle means to say the from where he started at that particular point he came back. So this makes it zero.
Initial and final positions
Okay.
as
Yeah. All right. And the next point is distance does not actually increase with decrease with time. Okay. If time is increasing, body is moving, distance will always increasing with the time. Okay. And for a moving body, as we have discussed, it will never be a zero thing. Clear? With the time, your displacement can be negative, it can be zero, okay? It can positive, whatever value, all values are possible for displacement, but yeah, it will never be greater than the distance value. Okay, so this was the thing. Mm, that's fine for now. Let's come up with a velocity. Okay, next is velocities. So what is the velocity? Yeah, so Bhavna, when we talk about the velocity, what is the velocity? Velocity is nothing but the rate of change of displacement. Okay? Rate of displacement, or you can say rate of change in position. Rate of change in position.
change in displacement by time is the formulas.
Change in displacement by time, you can say. Okay. Or you can simply say that rate of change of position.
Okay,
Rate
sir.
of change of in the displacement, let's say. Displacement. Actually, I think this is not a good statement. Rate of change in position is fine actually. Rate of change in position. Okay. With respect to any wait a second. With respect to time at any instant. Time at any instant. Now, Bhavna, what happens is I am giving you a some kind of velocity vector. Okay, it may be a variable velocity vector. It may be a constant velocity vector. In that particular case, if I give you velocity, you can simply say that. Right. Yeah, I have given you the displacement vector, not the velocity vector. So I can simply say that a velocity vector will be nothing but what is that? Rate of change in position, right? So I can simply say that delta S vector, okay, and delta R vector, no, delta T vector, right? Can I say this? This suggests final position minus initial position. This suggests final time, basically time at the fine when you are at the final point uh, minus time like initial time when you started your journey. Clear, Bhavna? If you say
Yes.
you are looking for a very short period of time, I can simply say that the velocity you can write in that case is, you know, Bhavna, for very short distances and something, we come up with a very small pieces, right? And this is a very small piece, ds, okay, and dt. So you can simply say this is the thing. What you have to do, you just have to do differentiation of s with respect to 2. Clear, Bhavna? Okay, and this
Yes.
also can be called as instantaneous velocity. Instantaneous velocity. Okay. What does this mean by any instantaneous? Assume Bhavna, this was your journey. Okay, from here to here. For this point to this point, you move with 2 meter per second. In this particular instant, you move to 1 meter per second, and so on for all journey. Now, if I generally ask you, what is the velocity when you move from here to here? So for this, you can see you have taken a lot of different kind of velocities, right? So you can't tell me one, you can't tell me two, because all of the part of
At
your
an
journey.
instant of time.
But what you can do in these cases, you can give me the average. Sir, I will give you the average of the velocity by which I have moved. That is fine. From that, I am going to get the average velocity. So you can simply say that this v which we have written over here, if your velocity is constant for path, the average velocity and the real velocity is same. Okay, if you have changed your particle from time to time, you can simply write this as average velocity. Okay, this will result with the average velocity. What is this instantaneous? Now to get this one velocity, I will specifically ask you, give me the velocity at a instant of time. Okay, at that particular instant of time. So this is that particular instant of time. I will give you the time value and ask you at this time what was your velocity. Okay, so you can simply go and yeah, that's fine. Okay, we are done with the instantaneous time.
So it's 550.
5:50. Bhavna, you joined late or what? Okay, actually
So
today I started.
maybe.
Yeah, you joined also late. I started 5 minutes late, but you didn't join that time. Okay, no problem. So, okay, I can end the session.
It's my
Mm,
college time, so
okay, fine. So I will end this session. Okay,
okay,
yeah, Bhavna. So that's all. Bhavna, in the next class, please try to join on the time, okay? Because it's just
okay,
45
sir.
minutes, and if you just make 10 minutes late, so we are left with 30 minutes, okay? So
Okay,
that's it.
sir.
Okay, fine. I'll end the session. You can leave. I'm just pausing PPT.